When we think of thermodynamics in action, we picture raw, kinetic power. Expanding steam slamming a massive steel piston forward to drive a locomotive. But capturing the exact physics of that power is incredibly difficult. In the real world, when gases change states, like expanding rapidly into an open space, they move in a chaotic blur of non-equilibrium. During rapid shifts, temperature and pressure are uneven. Hot, high-pressure molecule clusters swirl on one side, while the other remains cooled. This makes it impossible to define the state of the gas, calculate heat flow, or measure work. To bypass this chaos, physicists created a mental workaround. They designed an idealized, perfectly controlled environment to slow down the motion and track every microstep as a system moves from one state to another. Analyzing the massive output of a real engine requires us to first master a theoretical slow-motion universe. This environment is built on the quasi-static process. Literally meaning nearly static, it describes a change that happens infinitely slowly. Imagine a gas cylinder with a piston. Removing the weight 1 grain of sand at a time allows the gas to expand fractionally and settle into perfect equilibrium. At every micromoment, its pressure and temperature are uniform and precisely measurable. This patience creates a mathematical sandbox, allowing us to apply the laws of physics to a moving system without data being lost to turbulence. Inside this sandbox, we map out 4 pathways by locking one variable in place. First is the isothermal process, where temperature is kept strictly constant using a massive heat reservoir. Second is the adiabatic process, completely isolated by thick walls to prevent any heat transfer. These 2 paths define the thermal extremes. The isothermal path demands perfect energy exchange with the environment, while the adiabatic path demands total isolation. The third constraint is the isochoric process, where the volume of the gas is permanently locked. Because the piston cannot move, the gas cannot expand, meaning the system does absolutely zero physical work on its surroundings. Finally, the isobaric process maintains perfectly steady pressure. Even as the volume changes and the piston rises, the internal force remains fixed. By isolating each variable, we have successfully divided the chaotic behavior of a real gas into 4 predictable, calculable models. These 4 quadrants provide a unified framework for navigating any change in state. Labeling a process identifies the mathematical behavior of the gas. It tells us exactly which variable in the first law of thermodynamics can be ignored. In an isochoric process, we can immediately remove work from our equations. In an isothermal expansion of an ideal gas, we know the change in internal energy is 0. These labels remove the guesswork from the calculation. While a real steam engine is violent and fast, engineers can approximate its stroke by summing thousands of these tiny equilibrium steps. This integration allows us to move from an ideal model to the specific math required to size the massive mechanical rods and gears shown here. Each named process tells you what stays fixed during the change.